much. Yeah, so this is me. This is the title of my talk. I'm a principal engineer on the search solutions teams. And this is Jeroen Bos, a 15th century painter from the south of this country who liked fantastical creatures and will be joining us for a bit of this journey. This is the type of painting he made, which is bizarre and amazing. I think this one is in Madrid, in the Prado. But yeah, I love these paintings. So I will talk a bit about the evolution of search the past year or so, and then give a bit of a hands-on demo on some of the APIs we've been working on and show you how easy and how complex we can make search. So how search has changed, this is kind of the evolution we're seeing. We started with textual search, which is the bread and butter of Elasticsearch. That's what we grew up on. Vector search has come into play more the last couple of years. You've actually been able to do that for quite a while in Elasticsearch, but it's really come to prominence in the last year, I think. Hybrid search is what you're seeing more, where you're combining the two, and then relevance tuning comes on top of that and makes it, makes the relevance better, which is what we're all after when we do search. So text search, I hope you're all familiar with that. BM25, this is what Elasticsearch does. Keywords, you can do precise matching or more fuzzy matching, and this is the basis of almost all search you see online. That works well. Vector search, on the other hand, translates both data and queries into vectors, so arrays of floats, essentially, and then tries to compute the similarity between a query and the data you're searching over and try to find the best match that way, which is a very different approach and tends to be better at imputing meaning, but worse at getting at specific keywords. So that's kind of the trade-off you're working with. And there's a combined approach, which we advocate because it tends to work really well, where you combine the scores you get out of the BM25 keyword search with the scores you get out of a vector search you're doing, combine them, and then you tend to get better relevance, and you get the best of both worlds in many cases. Not all, but in most. So this is kind of how RRF works. On top of RRF, we've added support for reranking recently, or easy reranking. You could always do it, but made it a little easier. Reranking happens usually at the final stage or the mid stage of a search query. So you execute a query with keyword search or vector search or a combination of the both. You get back a set of documents that have been scored, and you may use a more complicated or more computationally expensive machine learning model to then re-rank what you see. So maybe you get 100 docs back out of your initial search, and you want to make sure that the top docs are the very most relevant ones, and you use a more expensive machine learning model there because it's only over 100 docs instead of your entire database of maybe millions of documents, right? And we see this a lot in web application searches and in RAG use cases particularly. So what we've built recently to make all of this easier is the Inference API. So this allows you to, and I will show this in a bit in a demo, easily use all of these types of search, of vector search at least. So you can do re-ranking, you can do sparse vector, dense vector, and you can call third-party services like ChatGPT or Cohere for re-ranking or other kinds of services to easily work this into your search application. It's easy. For instance, an inference re-rank, you could just call _inference/re-rank with the model, give it some documents, and it will re-rank those documents for you. Retrievers is the other core part that I will show you hands-on in a bit, which makes combining all of this stuff a lot easier than it used to be. So you used to have to do a lot of math and a lot of explicit things inside of your query to be able to do these things. Retrievers make it a lot easier to nest different queries, combine them with RRF, and then add a re-ranker on top and keep nesting until you hit kind of the relevance you really want to hit. We use a couple of terms for this. A retriever is any kind of query thing that retrieves documents. That's why it's a retriever. A source retriever grabs stuff from the source. A compound retriever takes the results from source retrievers and combines them, compounds them into a second set of documents. And then a re-ranker reorders the documents that you got from the first couple of retrievers. This is kind of the syntax for a retriever. I will show you this in more detail in a bit. but you can see kind of the hierarchical way this works, where you have a top-level retriever, then you have a re-ranker, that is the property of the retriever. Then the re-ranker contains a retriever, which contains an RF, which contains more retrievers, and that is how this works. So you have the inner stuff that retrieves from the source, RF that compounds this, and then the text similarity re-ranker that re-ranks what you have there. This is kind of the execution layer. So as you can see on the left, you have the index, you have the source retrievers that retrieve the documents, the compound retriever that compiles that into a separate set of top documents, and the re-ranker that re-ranks that again. And maybe you want to add a third re-ranker or fourth or whatever. You can keep going as long as you want. That's all up to you. So models are lazy, it's fun, but not what I want to show you. So the way this works, let me do this first, and that might take a time. So what we have in Elasticsearch is inference endpoints, and we ship by default with two, one for ELSER, which is our internal sparse embedding model, and one for E5, which is a model we endorse, E5 small, which is multilingual and does dense vector embedding. So these are available out of the box. They are, I think we made them first available in 8.16 or 8.15, off the top of my head. 8.15? Yeah. And in serverless, which, by the way, I'm doing this on. It's available now because everything hits serverless first. So this is the mapping I'm using right now. I will show you how easy it is to execute simple semantic search. I've added two semantic search fields. So we have an ELSER field here, which is of type semantic text, and the inference ID is the inference ID we ship with, which is ELSER2 Elasticsearch. And an E5, which is a dense vector field, but you don't need to know that. You also don't need to know that this is a sparse vector field, because we take care of that for you under the hood. So again, this is the E5 small. And the way this works is we have a title field and a description field that are of type text, and that we copy to both of these inference fields. The copy to copies the text. As soon as you index it, Elasticsearch knows, hey, I need to execute inference on these with these models, and it'll index the vectors with them. So this might take a little bit of time, because I think the model needs to spin up, because this is on serverless. And there we spin to 0 unless we explicitly say, hey, you need to stay up. So there's a minor chance that this might time out, but that's OK. It'll work. It just takes a bit of time. You can set it to be always on and have a minimum allocation of 1. It'll never spin to 0. I didn't do that because I wanted to show, hey, we can spin down to nothing and then spin back up. Yeah, see, that timed out. This one should work now, because probably the spinning up is done. Usually it takes about a minute or 2 minutes. Yeah, the one's done. And make sure this one also got indexed. Yes, this was already there. Cool. So one thing that does that's really cool is this automatically chunks text for you. So you can see that the first docs I indexed was the Alps. We have chunk 1, which is just the description, and chunk 2 is the title, because I copied both of them. If I had indexed a really large bit of text, it would start chunking it into bits of, I think, 250 words by default, and then produce vectors for each chunk. So obviously, you can do traditional traditional search, text search. Slightly different concept. And if I search for Rocky Mountains, this thing will think, hey, you want to know about the Rocky Mountains, right? And that's the only result we get back. But maybe, actually, I want to know about mountains that are rocky, which this thing cannot know, because the Alps are not described as Rocky Mountains, even though they are. If we do a semantic text query, which is as easy as this, just a query type of semantic with a text query, and then the field you have the vectors in, you get back Rocky Mountains as obviously the top doc, but you also get back the Alps, because semantic search is smart enough to understand the meaning and not just the actual keywords you're using. And what's also cool is we can explain this. So if we do an explain on here, we see a lot of math and a lot of stuff, and I'm not going to show you everything. But what you can see is, hey, this is the Rocky feature. So the model knows about a thing called Rocky, and it found that in both of these things. Same is true here. So the next one is mountains, and then we can keep going. A mountain, I think there's volcanic and a bunch of other stuff. But you can see every feature it hit, which gives you a lot of ability to kind of explain and understand how does this model work, what does it think is important about this query, and what is important about the docs. Right. And I can do the same with retrievers. So building this with a retriever, the only thing I'm doing is kind of wrapping this with retriever and standard, and then we do the same thing. This is just basically some syntactic sugar around it. That's not very interesting. But what we can do that's much more interesting is merge semantic search and full text search. So that's the RRF, the reciprocal rank fusion I talked about earlier. You do it very simply. You have a top-level retriever of type RRF, and that contains an array of retrievers that do what you want it to do. So we have a standard retriever, which in this case is a multi-match query with a boost for the title, and then a standard semantic query with just the query in it. The rank window size of 100 does nothing because there are 2 docs, but you know. And then you get this, which the result is the same, but you can see how the syntax works and how easily you can kind of put this stuff together. And highlighting also works, which is kind of cool. So you get Rocky and mountains get highlighted here, and in the Alps, nothing gets highlighted because there was nothing to highlight from the query. But you can still, like all of the main features of Elasticsearch still work when you use retrievers, when you use RRF, when you start compounding all of this stuff. And we can ask it to explain the RRF too, which gets you a really, really long, really complicated result that I won't go into too much. But you will see the explanation for each of the term frequencies in here, and then further down you will see the semantic frequencies, and then the result of the computation as well. So again, we can explain everything for you and tell you this is why the result happened. It's not just a black box because it's a vector search model, right? So something a little more interesting. And now we get back to why I talked about Jeroen Bos. I crawled the whole Rijksmuseum website on Friday. I did almost no data cleaning. I did very little to make this better. So what you're going to see is very raw results with a bunch of suboptimal results. But we'll get that. This is the mapping I used for the Rijksmuseum. So we have a body, which is the body of the web page that I crawled. We have an elsewhere field, which again is a sparse embedding field. And then I have a dense vector nested field that I ingested the dense vectors manually into. And what's interesting here is that this uses E5 large, which has 1,024 dimensions. And usually that's kind of prohibitive in cost in terms of search. That takes a lot of memory and a lot of storage. But I'm using better binary quantization, which we released just now, I think in 8.16. On serverless it's available. And that makes the memory requires much smaller and much faster to execute while still getting pretty decent relevance results. And we'll see that in a bit. So I think we have about 78,000, 75,000 results in this index, which is not a ton, but it's good enough to show you kind of what happens, right? So I am interested in paintings in the cells of Jeroen Bos. Now, Jeroen Bos, the Rijksmuseum has 0 paintings actually by him, which is a bit of a shame for the largest museum of the country, but they don't. But they have a bunch of stuff that is like it, and I want to know, hey, which paintings do I go see if I want to see more stuff by him? So this is just a traditional keyword search. You get a bunch of results that aren't super interesting, like Dutch paintings of the 17th century, which is the wrong century, a list of paintings with Frans Hals Prescott for some reason. This one is more interesting, and then a workshop chemistry, another list of paintings, Secrets of the Milkmaid, which has nothing to do with it. So you get some relevance, mostly on the title, but very little else. And a few that are not at all relevant, like this one, which is just a sculpture that happens to be from Den Bosch instead of by Jeroen Bos. Semantic search, we can do another thing. We can boost the title, and that gets you maybe slightly better results, but not significantly more. If we add semantic search instead, we get different results. So we get a lot of results that just say Rijksmuseum in the title, and then a couple that are less relevant. Like this one's here because she was married to someone named Johannes von den Bos, which, again, not relevant. But if we go to a couple of these, you will see that actually this is relevant, because this is a copy of a Jeroen Bos painting. And the keyword search did not pick this up. Like the keyword search just plain did not see this, and the semantic search did. But semantic search missed a bunch of stuff with obvious titles in it. So there's like a mixed bag there, right? And both of these results return a bunch of stuff that's not relevant at all. And again, we can explain this and figure out why. And actually, hey, there's a Bos feature, and I have no idea what this Bos feature means, but the model knows it, and the model thinks, hey, this is an important feature in these results. So what happens if I do RRF on this stuff? I combine the semantic search with the keyword search. Does that yield better results? Well, yes, actually. So suddenly we get the titles back, right? The ones where obviously this is relevant because this is a copy after, or is in the manner of Jeroen Bos. So these are the ones I really like to see. And you get the same results from semantic search I saw earlier that do not have the title, because their title is just Rijksmuseum, but they do have the content that I need, which is, again, this kind of stuff. Right, again, this is a manner of Jeroen Bos, cool painting. This is what I really want to see. So we did very little. We did no tuning on this. And the results are already much, much better by using RF, just semantic text, and a keyword search. As I said, I did no cleaning, no data, nothing. This is just very basic, right? And we can, again, explain this, and you get the very, very complicated, very, very, very long result that you can try parsing if you want. I'm not going to do it for you. Now, we can do a third thing. We can add a dense vector search. So remember, I said, hey, I indexed a bunch of vectors. I did better binary quantization, which should make it faster. That also means I need to oversample, because better binary quantization loses a lot of information. So you need a large sample size to be able to get a good number of candidates. And we can plunk this into the same RRF. So we still have our keyword search, we have our semantic search, and now we're adding another semantic search, but an explicit vector search using KNN on a binary quantized field. And again, we're getting more or less the same results. I think these are slightly better when I looked at these, but nothing irrelevant, and everything seems, well, pretty good to me. So what else can we do? Well, we can always add a reranker. Maybe that will help, and rerank has gotten very easy again. We just shipped the Elastic rerank, the very first version, in serverless, not in 8.16, but this should, I think, actually I'm not sure if this is going to hit 8.17. It might hit 8.18 instead. I don't know either. But you can already do this in serverless, and it will give you this. So you can do, if you execute this, I executed this earlier, so I don't need to do it now. You get a inference endpoint that you can run rerank on. So we can do things like, hey, here's an array of different things. What's the question? What is the capital of the USA? And we rerank this, and ta-da, Washington, D.C. is on top. And then we get Charlotte Amalie and a bunch of other stuff, and way at the bottom is capital punishment, because that has nothing to do with the capital city. So that's how easy reranking is if you have a limited number of docs, and is really fast. So again, we can wrap our really complicated query from earlier, which is this thing, in a text similarity reranker. So again, top-level retriever, type text similarity reranker, and then underneath that is a retriever with RF, so that is actually the source of all of our documents. And then we add, hey, what do we want to re-rank on? So I want to re-rank on the title field with maybe 100 rank window size, the inference ID, and the inference text. And what do we get now? Well, on the title field, I get 3 results that are really good. This is exactly, seems like the most relevant and the most important result. And then I get a bunch of nonsense, because the model decided that everything below this score is not relevant, and we're just going to drop it, which is not great, all right? And this kind of shows you, hey, you need to play around with these things and figure out, do I need a re-ranker? Maybe you don't, maybe you do. It really depends on what your use case is. And you need to start testing and evaluating these results. You need to find a way to get feedback and incorporate that feedback into what you're doing. There's one final step I can take. I can also feed these results into an LLM quite easily. So again, I created an inference endpoint for OpenAI earlier. Then I can ask questions. So hey, I can ask it what is Elastic, and it will tell me, hey, this is what Elastic is. What I can also do is feed it all the results from the compound re-rank query I ran earlier, and then see, hey, can you summarize this stuff for me? Because there's a lot of information in here that I don't care about, like, hey, the cookie usage that gets prepended to almost every crawled site. So give me the core of what's happening here. And this is essentially what RAG is, right? We executed queries, we got the most relevant documents, or we thought were the most relevant documents, and we ask an LLM questions about those documents. That is what retrieval-assisted generation is. So, hey, it summarizes the first one, the second painting, the third painting, and then correctly says that the rest is completely irrelevant and you should ignore it. So actually, this might be interesting to show a user who executes the query. You go to this, you give them a summary, and then the summary can ignore whatever else isn't relevant in the result set. All right. Now, let's go back to this. So what did we learn today doing all of this stuff? Data cleaning is important. There's a bunch of noisy data in there. There's a whole bunch of irrelevant stuff that made it much harder to get good results. Semantic search is also not magic. Actually, the initial keyword search wasn't bad. It got pretty decent results. And if you actually look at all the semantic searches we did, a bunch of it was actually a duplicate of what the keyword search already got. It's just that all of those duplicate documents were in the result set, both with a good title and with a bad title. The other thing is that we should be evaluating these models, the queries, and the results over time for each use case. This was a fairly random use case I chose, and I put very little time in trying to refine it. But if this was a production set, I would want to evaluate user queries, what are the most common queries, what are the most common things they click on, use that to feed back into the kinds of queries or the kinds of compound retrievers I build, maybe the kinds of models I select, and evaluate what happens there. So try to use your users' queries and their behavior to evaluate your search. I think Alex Krills is talking later today from Kaufland, who might touch on that as well, because he touched on it yesterday, which is actually a really interesting talk. And all of this, what I did today, is about trade-offs. So the more complex you make the thing, the more you add to cost, the slower the result is going to be, but maybe you'll get better relevance. And every step in this, you have to evaluate, hey, can I take this out? How important is it? How much is this improving my relevance? Is that worth the cost I'm putting into it? Is that worth the speed it's costing me? So as always, all software engineering is about trade-offs, and that's also what vector search is about. And this is, for me, the main result I got out of this. I did not know this painting. I think it's really cool. I have no idea why this nun has a weird, like, kind of hay barn on her head, or what else is going on here, what this weird-ass flying thing here is. I don't know. But I think this is really cool, and I'm glad that this exercise taught me about this painting.